Hello, and welcome back to my webinar series on the C++ standard template library by example. What we're going to do today is talk about some of the other interesting aspects of C++ templates, particularly focusing on templates as they're applied to classes, although we'll also spend a little bit of time talking about some really cool features of variadic templates and how they're applied with C++ functions. So without any further ado, let's go ahead and jump in. I'll show you the code first, where we're going to be covering today, and then we'll look at the examples. So let me share my screen, and you can see a couple things. So this is where the code resides. We're going to be looking in my C++ STL folder in the S-02 subfolder. And we're going to start by doing a revisit to one of the examples we looked at yesterday, just to kind of clarify a few of the interesting aspects of that example. And then we're going to go ahead and talk about some brand new stuff. So let me go ahead and share my IDE. As you can see here, here's the example we were looking at yesterday. This is example 2.4a, and this was demonstrating template specialization. So if you recall, we had a particular template that we were using as the basis for specialization. This is a very, very simple container that has a constructor and a method called increase, and it has a field called element, and it's parameterized by type T. So a very, very simple example. And what I was doing was I was showing how we could parameterize this with different types. So the examples we looked at were parameterizing this with int, we looked at parameterizing it with double, and so on. But those examples illustrate a couple of things that are not always the case. Number one, as you can see, int and double both have less than operators built in. And so one interesting question is, what happens if we try to parameterize this container with some user-defined type that doesn't have the less than operator defined on it? What's going to happen, number one. And number two, let's try to see some better examples of specialization that will do something above and beyond what the compiler could normally do if we just let it do the natural course of instantiating the template as it was defined. So those are the things we're going to look at today. So the first thing I want to do is show you what happens when we do an explicit specialization for a data type that would otherwise make no sense if we were to try to do it just by using the compiler's default instantiation mechanisms. And what we're going to do is we're going to instantiate a specialized version of container that works on char stars. So as you probably know, in C++, because it's as close to C but no closer, it leverages the char star features for dealing with kind of C-level strings. So a char star or const char star is kind of a C-level string type mechanism. And you can use that in C++ as well. But were we to try to do this without specialization, it wouldn't do what we're trying to get it to do. So we're going to make a specialized version of container. And you can see here we use the specialization syntax. We say template, less than, greater than, class container, and then we specialize it to work with char star, so pointer to character, which is an idiom in C and C++ that typically means basically a string, a built-in string. So down here we have an explicit container that takes a char star argument and stashes it away in our char star element data member. And then, because it doesn't really make any sense to increase a char star in the way it means to increase an int or a double, we're going to replace the increase method with another method called uppercase. So this particular method is completely new. It was not part of the original container. You don't see uppercase there. So this demonstrates one thing that you can override's the wrong word. You can define new methods in specialized classes. So let's go ahead and take a look at uppercase. And you'll see this is the kind of code that would never be synthesized out of the box by the C++ compiler if we just let it do its natural instantiation of this container template for a char star. So what we're going to do is we're going to define uppercase to walk through the elements of the character array, and then we're going to look for all the characters in the character array that happen to be lowercase characters, and we're going to uppercase them. So that's what the logic is here in this little loop. And then when we're done, we return the element, which has now been uppercased. So if you take a look down here, when we do this, you can see that we have a lowercase character array called hello world, which is basically a string in C-level parlance. And then we go ahead and pass that to my char string, which is the template instantiated, the specially instantiated, explicitly instantiated version of the container. And then when we say my char string uppercase, it goes ahead and uppercases it. So let's go ahead, let me comment out this piece of code here just for a moment. Let's go ahead and run this thing just to give you some confidence that it actually does what I'm promising it does. And as you can see here in the output, we get hello world instead of hello world because we've uppercased it. So now it's shouting at us. Okay, so that was one thing. That's kind of showing perhaps a more useful way of doing specialization. So we're specializing on something you wouldn't really get out of the box if you just did the char star by itself. The second thing I want to do is I want to show what happens when we instantiate an object that initially does not have a plus plus operation defined on it. Because if you go back and you look at the implementation of container, you'll see that the increase method is expected to be able to do a pre-increment on element. So if we try to instantiate this with a class that doesn't define the plus plus operation, then we'd expect bad things to happen. And that's exactly what's going to happen. So as you'll see here, here's our initial class we're going to use to instantiate the container template. This is foo, wonderfully expressive name. And what this does, just ignore the commented out part for the moment. This is going to have an explicit constructor that takes an int and stashes it away. And it has an explicit conversion operator that will go ahead and convert a foo to an int. And I guess we should probably not do the plus plus operation here. Let's just do this. And so now we have kind of the basic bones for something we can instantiate in our container. But you'll notice that at the moment, there's no plus plus operation defined. And in fact, when we try to say my foo, we give it a foo with 10. We try to call the increase operation, it's going to yell at us, the compiler will yell at us, and it'll say, can't increment the value of type foo, because there's no foo that's defined to allow incrementation. So one solution to this is to go ahead and define operator plus plus. And this is the syntax for the pre-increment version of operator plus plus. There's also a post-increment version we'll talk about at some other point. So as you can see here, just to make it clear what's going on, we're going to print out what the method is it's being called. It's foo's operator plus plus. And then it goes ahead and it makes a new foo that contains the pre-incremented version or value of the data member I. So now, with that uncommented, now you can see the code is happy. And when we compile it and run it, it should go ahead and take the 10 that was passed in and increment it. So you can see we get 11 out of here. And we call foo operator plus plus. Okay, so far so good. So that's one way to solve this problem. But there are other ways to solve this problem as well. So here's another alternative. What we're going to do here is we're going to define a specialized version of the container that explicitly is designed to work with a foo. And so what we're going to do here is we're going to have a container that takes a foo argument, stashes it away, specialized. And then we're going to define the increase method, which is going to return a foo. And what we're going to do here is we're going to print container foo : increase. We're going to let you know that this is the one that's being called. And then we're going to go ahead and call the plus plus operator. The plus plus operator, of course, is going to call the plus plus operator up here. And that's going to go ahead and increment the contents of foo. And so let's go ahead and run this, and then we'll see what happens. So now you can see the code compiles again, but now we're using the specialized version. Let's hope we use the specialized version. And so if you take a look at that, you can see that it called container foo increase, which is this specialized method here. That then called plus plus on foo, which again calls this operator. And then you'll see at the very last thing we do is we go ahead and we output the incremented foo. And that required us to define an extraction operator that's going to go ahead and get the value and write it to the stream. And that's what this thing is. And you can see that we define it to take an OStream reference and a foo. And we probably should have been a little smarter and said const foo. That's probably a better way to do it. And so then what we're doing here is we're going ahead and we're explicitly casting the foo to be an int, and that under the hood will trigger the call to this particular method here. So that'll go ahead and do that. And I probably should say this is a const method. And if we do that, then I can probably come back here and make this a const foo. Oh, well, I'll go ahead and mess with that a little bit. So we'll play around with this and get that right. But the bottom line here is that we can pass foos here, and that's how the output gets dealt with. Okay, so that kind of wraps up that example. I just wanted you to see what happens when you define your own type, and then you have to make sure that it has the operations that are expected in the template in order for the right thing to happen. Okay, so let us now go and move on to a new example. And we're going to go here. I think we left off at the example 7. So the next example is example 2.8a. And this is going to show one of the reasons why templates are so great, because they work around annoying problems with macros. Back in the bad old days, days of C and the days of C++ before templates, which occurred for about 5 or 6 years in the, actually more like 10 years, I guess, in the 80s, C++ didn't have templates. So if you wanted to do generic types of operations without defining a gazillion overloaded methods or overloaded operators, you had to use macros. And I'll show you an example of a macro. And of course, the point of this is macros are evil. There are very few things that they're good for, and this is not one of them. So here's a macro that attempts to define the min of 2 parameters. And what it does is it says min of ij, and then it goes ahead and it defines this very convoluted looking expression with lots of parentheses. And the parentheses here, of course, are necessary to make sure things are grouped properly and they're performed in the right order. And whenever the min macro is used, that whole expression is just going to be substituted with the parameters I and j. Just, it's kind of like cut and paste, if you will. The preprocessor, which is what processes the macros, does the cutting and pasting. Okay, so there's a problem, and let's take a look at why there's a problem. So here we have the example. We're going to have A and B, and we're going to start A at 10 and B at 20. And then we're going to go ahead and call min, which is the template function, which we'll look at in a second, with A++, B++. And then we're going to call min, which is the macro, also with A++ and B++. And what will happen here is we'll get very different results. So let's go take a look at the template version. Here's the template version of the min macro. And you can see here how it takes a const tref I and a const tref j, and it goes ahead and just uses the famous ternary operator to check to see which one is the min. Is it I, is it j? So that's pretty much the same logic as we see in this macro, except it's got fewer parentheses, and that's a good thing. But more importantly, the semantics of min follow the semantics of a normal function once it's been instantiated. So once it's instantiated with the types, in this case int, then calling the min function is just like calling any function. And what I mean by that is that the arguments are evaluated once at point of call. So what we'll get here is we'll get min of 10 and 20, and then A++ and B++ will increment A to 11 and B to 21. But what gets passed to min is 10 and 20, because those are the values before it was incremented. It's a post-increment use of the ++ operator. Conversely, the version down here, this min, this will actually get expanded in line to look like what I show here. It'll be A++ less than B++, A++, B++. So the values are going to get wildly updated. In fact, just for kicks, let's go ahead and write the output here. So we can say A equals, and then we'll say A, and we'll say B equals, and then we'll do B. And this will also show that a lot of extra stuff happening here underneath the hood. So let's go ahead and run this code, and we'll see what the results are. And they're not what you might think unless you already know the semantics of macros and how bizarre they are. So you can see what we get here is we end up getting the min of 10 and 20 is 10, which is what you'd expect. But then when we do this min, we get the value 12, when in fact it should really be 11, should by the normal function call semantics. And that's because it's expanding into a++ less than b++ question mark, a++ b++. So it's having all these extra side effects because macros are just mindless text expansion. And then when we're all done, you can see that a++, or sorry, a and b are now 13 and 22. So this macro has ended up having side effects that are somewhat surprising if you don't understand the weird semantics of macros. So the long and the short of it is, there's only a handful of things that macros are still good for in modern C++. And those things are typically include guards, things like making sure the header files aren't included more than once, making sure that template C++ body code is not included more than once. That's one thing macros are good for. And they can also be good for setting parameters at the make level or the command line level that you want to use to set certain default values or comment out certain parts of code or selectively compile certain parts of code. Those are really the only things that macros are any good for at this point. So just wanted to show you that. It's important to understand why templates are often a great replacement for macros, and you should really never use macros in this kind of generic function-like model anymore because templates do a much better job. Okay, let's move on. Let's go ahead and take a look at another example. And this particular example is going to demonstrate some things that it used to be really important for C++ back when the template implementations were in their infancy, back in the sort of early to mid 90s, and maybe actually a little bit later. Because back in those days, the compilers would often have bugs in them, and the bugs would manifest themselves as follows. So I think I mentioned before with templates, the compiler is supposed to only generate code for methods that are actually used. So if actually used in the source. So if you had a template with 200 methods in it, and when you instantiated it, you only called 2 methods, those 2 methods would be instantiated, but the other 198 wouldn't be. Well, back in the bad old days, compilers would get confused, and sometimes they wouldn't generate the templates correctly. And so there was a kind of a workaround for that can still be a bit useful, especially for testing, where you can basically have templates that are going to be explicitly instantiated. And nowadays, this is much, much less needed because linkers and compilers are a lot better. But back in the day, they were an issue. And so let's take a look at some examples of how you can explicitly instantiate templates. And this is kind of cool. It also gives us a chance to talk more about some of the introspection mechanisms that are built into the C++ type system. So we have a little method here called print data type that takes a data object and goes ahead and prints the name of its type. So that's just it's kind of a little quasi-reflective like mechanism, but it's not nearly as powerful as Java reflection. So let's go ahead then and define ourselves a class. So we have a class called example class. And we can also use a default constructor. This is a syntactic sugar feature that was added in more recent versions of C++. If you have sort of a no-op constructor like we do here, you can just say, compiler, generate the default value for that. So you can see we have a default constructor, we have a method called result, and a method called add. And that's just there to kind of make everything work together. And this is a template class. So now what we're going to do is we're going to come down here and we're going to tell the compiler, I want you to explicitly instantiate function templates for print data type for ints and doubles. So that forces the compiler to generate that code. Then we can also say, I want you to generate the constructor, and I want this constructor to be generated, but for int. But you don't necessarily have to generate anything else unless I use it. So that's forcing the constructor to be generated. We can then go ahead and say, I want the entire class and all of the methods explicitly instantiated for double. And then down here, we can do the constructor for string and the add method for string and the result method for string and so on. So you can mix and match and pick and choose what you want to generate. And then down here, we go ahead and basically do the instantiations. Now, this, of course, should generate the code to do the right thing. But normally, it wouldn't generate the code for those methods unless we actually use them. But we've instantiated them using the compiler's explicit instantiation feature. And then just for kicks, we go ahead and print out the data type name for an example class of int and an example class of double. So let's go ahead and run it just for kicks and see what the results are. Oops, didn't like that. Let's go fix that. Compiler was trying to be too clever. Let's try that again. All right, so you can see what it does is it goes ahead and prints out the name of this class, and the name is example underscore class, and then it says it basically is has, I think it says 13 characters in example class. That's just prefixing it to make it sort of unique among other classes with similar names. And you can see it's parameterized by int, and it's parameterized by double. So that's where the I and the D come in. And so this is just the way that the compiler encodes that. And that's actually relevant for other things like the way in which you can do type safe downcasts and so on, and various other more dynamic mechanisms for doing virtual method tricks. But that's not important for the discussion here. So that's just a silly example just to show you how you can instantiate various templates. Mercifully, most compilers will not have these problems anymore, so this is kind of only important if you're stuck using older versions of C++. Okay, next topic. Now that we've talked about kind of the basics of templates, I'm going to spend a little bit of time talking about more sophisticated uses of templates. And I apologize in advance. Some of the topics here are quite advanced, and they assume that we've talked about other things in more detail, things like containers and things like iterators. So don't worry if you don't understand all this stuff. We'll cover all this other stuff later, but I just think it's really fun to show these advanced template features, and this is kind of a good place to show them because we're talking about templates. Okay, so here's the first example. This is demonstrating the concept of basically variadic templates and template recursion. So if you're familiar with older style C operations that were variadic arguments, things like printf, you would have a format string and then you could give parameters after it. Printf and its ilk are extremely error prone and considered very bad practice these days. So C++ has solved those kinds of problems in a type safe way using something called variadic templates, which are basically just templates that can have an arbitrary number of parameters passed to them. So let's take a look at a couple of different examples. This is really fun. So we have a method called adder, and this is the base case for variadic template recursion. And all this is going to do is it's going to take the value that's passed to it, that's a template parameter, template t, and return that value. So it's very simple. Then we're going to define an overloaded version of adder that has a variadic template argument. And variadic templates are just going to be used or described as having the ... after the type name. So this says adder takes a first parameter of type t, and then it takes an arbitrary number of other parameters of type t. And the way it gets expressed here is we have adder, which takes t, which is first, and then we say args, which is the variadic template definition, ... and then we just give the name of the parameter. We call it args here. And then what we do if we want to use this thing is we say first plus adder, and then we pass args ... into that. And as we'll see when we run the code, the compiler will go ahead and basically recursively call this thing, essentially chopping off one element each time it's called, depending on how many elements are passed to it. So it's kind of recursion, and here's the base case for the recursion. You'll also see that there's a really cool built-in macro called pretty function, and that'll actually tell you what function is being called and what the arguments are. And so we'll see how that gets to be used in a second. So here's how this gets used. We're going to start out by having a call to adder with 1, 2, 3, 8, 7. I don't have to have 5 parameters. I can have 1, I can have 18, I can have 42, it doesn't matter. And then we go ahead and say the sum of calling the adder is whatever the sum is. And then just to demonstrate that this concept also works for other data types, we're going to go ahead and have one that has a bunch of string parameters. So we define a bunch of strings. C++ is cool. And then we go ahead and basically call the adder method to add those things all together. And all that's required here is that there's the plus operation defined on the data types. That's all that we're requiring. And then we're going to go ahead and print the sum of the string. Seems kind of funny, but that's what we're going to do. All right, so let's go ahead and run this, and you'll see what we get. It's really cool. So you can see that the sum of the parameters we passed, the variadic number of parameters, is 21, and the sum of the string parameters is the string. C++ is cool. Now, the pretty function macro helps us see what's going on here. So you can see the first time that we call, let's see if I can make the run stuff be a little bit smaller. Let's say, there we go. So you can see the first time that we call adder, we have the first parameter, the t, is an int, and then we've got 4 more ints. And then that goes ahead and recursively calls it after stripping off one of the elements. So then we have a first parameter int, 3 parameters of int. Then it calls it with the first parameter int, 2 parameters of int. Then it calls it again recursively with the parameter int and 1 int. And then finally, we just have 1 int, and that's the base case of the recursion. That's this adder up here. And so what's happening is that those are all being called, and then it's summing the results together, because it's adding them with a plus operation, and that returns the result. And the same thing's happening with the string. It's just that the string is a bit more verbose, so a little bit harder to see, literally see what's going on. But that's an example of variadic template processing with C++. So everything's type safe. It's all handled magically underneath the hood. We'll look at some other more realistic examples of recursive templates and variadic templates in just a minute. Okay, now let's go ahead and take a look at another example. This example shows one of the most interesting and very common uses of so-called template metaprogramming, which is the ability to be able to program things that are actually evaluated at compile time by the compiler. And this is a really cool example. So just for kicks, we're going to compute factorial, and I'm going to compute factorial up to 20, which, as you can see, is a pretty daggone big number. And in fact, it's so big I have to represent it as a long. So factorial 20, it's believe me, that's the factorial, although you probably wouldn't have memorized that. Here's just the classic recursive way of computing the nth factorial, or the factorial here. So we're going to pass in val as n, and if the value of val is greater than 1, then we recursively call this function, subtracting 1 from val, and then taking val and multiplying it by sum, and sum starts out at 1. So you can see we're going to basically subtract 1 off of val each time, and then we're going to multiply sum times val, and that's going to come back as a value, and it's going to be this wonderful recursive set of calls. And as you might expect, this is going to be a pretty daggone deep recursion. I probably would have been well advised to use a loop here, but I decided to do it this way just to show how it works, and to show also how it corresponds to the other examples we're about to look at. Okay, so that's just good old factorial calls, and that's done at runtime. Now let's look at 2 different ways to do factorial at compile time. We're going to make the compiler do this for us. One way to do it is to define a function to be a so-called const expr, or constant expression. And there's a limitation, the limitations in what operations you can do in the in const expr functions. You can't do anything, for example, we can't say cout pretty function. That should be disallowed, and that's because this has to be completely evaluatable at compile time. And you'll see it should yell at us. Non-const expr function operator less than is being used in a const expr function. So let's get rid of that. So this code will actually be evaluated by the compiler at compile time before the program runs. And you can see that that's actually the case, because we can go and generate the value for an enum, an enumeration literal called compile time generated value, for C factorial of 20, and then we can use a static assert to show that it's got the right value. And if this was wrong, then it would blow up at compile time, so the compiler would catch it. Notice that we can't do this because that's not a const expr function, it's just a regular function. So all that code is evaluated at compile time. Here's an even wackier way of doing this. This is using template metaprogramming, and this is kind of the hello world of template metaprogramming. What you're going to see here is we're going to define ourselves a factorial struct that's recursively defined in terms of itself. So factorial is going to be defined in terms of a recursive call through inheritance to the factorial struct itself. And this is a template struct, so it takes a long and a sum that defaults to 1. And very, very much like this C factorial function up here, it's going to subtract 1 off the long and then multiply long times L sum. Except this is all taking place at compile time. Down here, we have the base case for this particular template metaprogramming example. We have a struct called factorial for the value 1 that takes L sum, and it goes ahead and sets the enum to L sum. So now let's see how this thing actually gets used. So we are going to say factorial for 20 is going to be, that's going to go ahead and generate something. We'll talk about that in a second. And then we're going to take the value, which is an enum, and we're going to store it in a const. And then we're going to use a static assertion to make sure that that actually equals the factorial of 20, which it does mercifully. If for some reason, by the way, we were to change the factorial of 20, which would obviously be a very bad idea. Let's change this to that. Then you would see that these static asserts will fail because those things are no longer matching. Mercifully, we know what the factorial of 20 is, so we'll make it work properly. So what happens here is when we call factorial of 20, that actually calls this function with 20, and then it goes ahead and will have L sum default to 1. So that's going to basically be 20 minus 1, and then 20 times L sum, which is 20. And then the compiler, in its magic, will go ahead and generate another recursive call to the template, which is not a runtime thing, it's a compile time thing, which will then be, of course, 19, LL will be 19, and this will be 20, and that will take place at compile time, and it'll come back with a value which gets stashed here in this value enum, which we can then get there. So the final thing we're going to do is we're going to go ahead and have a main program that's going to dynamically compute the factorial of 20, make sure it equals what we think it does, and we're going to go ahead and print it. And the nice part is because of the magic of const expressions and template metaprogramming, everything works properly. Our runtime stuff works, our compile time stuff works, and it's a very, very fascinating example of template metaprogramming. Now, you are very unlikely to have to write code like this, but it's used heavily in libraries. And in fact, you'll see some of the other features we're about to look at are more for people building libraries than for application developers per se. Okay, let's move on to another example. This is a really cool example. This is going to demonstrate a whole bunch of different things. It's going to show how we're going to be able to essentially wrap arbitrary containers, well, not arbitrary containers, arbitrary sequential containers, and then be able to pass variadic parameters to them in order to instantiate them. Now, again, you might want to do this perhaps for debugging purposes. You might want to have a way of wrapping your containers to debug them. You might even want to do this to wrap your containers to make them thread safe. You could make a thread safe container wrapper here quite easily. This particular example is just to illustrate the point. So what we have here is we have something called a container wrapper, and the container wrapper has a constructor, and the constructor, as we're going to see here, is going to have variadic parameters. That means it can have an arbitrary number of parameters. And what we're going to do here is we're going to take the parameters that are passed to it, and then we're going to forward those variadic parameters, which I believe is called a template pack. And we're going to forward those to the constructor of whatever container we happen to pass in as a template type to this particular container wrapper. So earlier, I think in a previous discussion, we talked about template parameters. This is an example of a template parameter. We have type name T, and that's the type, like int or double or whatnot. And then we're going to have a template parameter, which is going to be a container that will be parameterized by type T. And we're going to default this to vector. We'll talk more about vector in our next class. Okay, so what you see here is we've got the container wrapper that takes a variable number of parameters, which we'll see how it's used down below, and it goes ahead and it forwards them to the constructor of this sequential container. All right, so far so good. So let's come down here and see how we actually use this thing. So we're going to have a container wrapper here, and it's going to default to vector. So this particular example, the first one here, will default to vector, because of course that was what was passed up here as the default parameter for our template. And what we're going to do is we're going to say, container wrapper, I want you to create a vector with 3 elements, and I want each element to have the initial value words. And you'll see how that gets used in a second. And then the second thing we're going to do is we're going to say, I want you to make me another container wrapper, this time using a deck, not a vector, and I want it to be working on const char stars, and I'm going to pass you the beginning of an array, a built-in native array, to a set of C strings, C-like strings, const char stars, called shapes. So we have shapes, which has 3 elements, and then we go ahead and say pass that in, and then pass the end iterator. We'll talk more about iterators later. Shapes plus 3, that skips to 1 past the end. And then we go ahead and print these results out. So let's go ahead and run this code, and you'll see what it does. And it's very, very cool. So we get, of course, Shakespeare's famous quote from Hamlet, words, words, words. And then down here, you can see that we print out circle, triangle, square. And then it tells us what operation is being called. We're going to instrument the output operation just to see what it's doing. And you can see here, for example, we have an O stream. That's what is being called here. We have a way of being able to take a container wrapper, and then we print the function call and the arguments. And then for every element in the container, we go ahead and write out the element. So we'll write out words, words, words for the vector of that string, and then we'll print out circle, triangle, and square for the one that was the const char star. And you can see, if you take a look at what's being instantiated, it's the OStream extraction operation, which is past a string and a vector. And then down here, the other one's past a const char star and a deck, which of course matches exactly what we passed down there. So really cool example. This again demonstrates the power of many things in C++. It demonstrates the power of template parameters, where you can default them. It demonstrates the ability to have variadic arguments and to be able to forward them to the constructor. So when we passed in these 2 arguments down here, 3 and words and shapes and shapes plus 3, those things got passed and forwarded unchanged, uncopied, unsullied to the constructor for the sequential container. Pretty cool. Now, this particular example illustrated the ability to encapsulate or wrap sequential containers, but they're not the only game in town. And when we get a little further along later this week or early next week, you'll get a chance to learn about other kinds of containers. And there's other kinds of containers called associative containers. And unlike a sequential container, which typically just has elements like a vector of int or a deck of doubles, associative containers have keys and values. So that little wrapper trick we used there wouldn't have worked for associative containers, but we're going to show how you can use that with just a simple enhancement to what we're showing here. So let's take a look at the example. We're going to define ourselves a vector of floats, a list of characters, a deck of ints, and a map of string to int pairs. Now, again, we haven't really talked in detail about these containers. We'll cover them a lot more, but just I think you probably have a good intuition of vectors like a dynamic array. A list is a doubly linked list. A deck is like an array where you can add and remove things from the end or the beginning efficiently. And a map is just an associative array that maps some key to some value. So that's a quick overview. We'll talk about that stuff later. And once we defined our corresponding vector, list, deck, and map, we then want to go ahead and print the contents. And we're going to do it 2 ways. The first way is kind of the old school way, a little bit verbose, but it works for everything. And this is to use iterators. And we'll talk a lot more about iterators. Every container contains factory methods that make a beginning iterator to the first element and then an end iterator to one past the last element. And so you can see we have begin and end here. So that's going to be very simple. Here's print iterator. As you can see, it takes an iterator as a parameter, and we have a start and an end. And iterators, as we'll discover, are intentionally meant to work just like built-in C and C++ pointer arithmetic. You can compare 2 iterators for equality or inequality. You can dereference them. You can plus them. Some of them you can minus, and so on. And in this particular case, we're just using them as input iterators. We'll talk more about that distinction later. So what this does is it basically walks through the range from start to end and prints every item and increments the start by 1. Okay, that's classic old school C++ templates and C++ STL. This example here, print container, is much more powerful, and it requires the use of variadic templates. And so you can see in this particular case, we're going to pass in the container wholesale. So we pass in the vector of float, so the list of characters, or the deck of ints, or the map of strings and ints. I should probably give it a better name. Maybe I should call this, let's see, MSI. How about that? That's a bit more intuitive, map of string to int. And so let's go take a look at how we can define that. And here's how we do it. Here's the print container function, which is going to use some very, very interesting C++ template features, including C++ variadic templates and other cool stuff. So what we're doing here is we're saying, I'm defining a container, and this container is then going to have value types and args. And so down here, here's the parameter that's passed in. It's a container that has value types and sort of optionally args. And this is going to work for the map style containers that have key value pairs. And then all we're going to do is we're just going to iterate through here from beginning to end, and we're going to go ahead and print every one of the objects out. And that requires us to define this little helpful extraction operator, which is going to go ahead and take a pair, which is what's needed for a map, and it'll go ahead and print the first element followed by the second element. That's only needed for the map version. So let's go ahead and run this. And you can see it chugs away a bit and then prints out the results. And the results are kind of interesting. So you can see here that we show the print iterator version, and then we show the print container version. The print iterator version is pretty straightforward. We just pass in an input iterator, which is just the good old normal iterator to float and vector, and it prints the values out. When we print the container, you can see it's much more interesting. So the container is going to have vector, the value type is going to be float, and then the args are going to be this allocator. We'll talk about allocators later. And that's the way it's going to be for all the sequential containers. So for print container, for list, you can see the container is list, the value type is char. For the deck, you can see that the container is a deck and the value type is int. When we get down here to the print container for the map, however, things are much more interesting. So for the map version, the container is map. The value type is string, because remember, it's a string to int mapping. And then the arguments are going to be int, because it's string to int mapping. And then there's some other parameters there as well. There's the operation that's used to determine whether things are going to compare less than or equal to, and so on. And then there's the allocator. So there's a whole bunch of other gobbledygook that gets passed as other parameters. But we don't actually really care about that. The compiler and the template instantiation mechanism cares about that, but we don't actually care about that. So that is by far probably the most interesting example that we've looked at so far in terms of advanced features for C++ templates. This is, again, variadic templates, and just showing all the powerful things you can do with variadic templates. Okay, we have one more example to look at here, and I'll try to do this quickly. It's also a really cool example. And then at this point, we'll be done with everything related to classes and class templates and function templates. And then we can get on with the really STL stuff, like containers and different kinds of containers and functors and algorithms and adapters, da-da-da-da-da. So this is a really fun example. This example shows how the C++ standard template library uses variadic templates in the context of passing parameters to functions that are spawned to run in background threads. Now, again, this is a bit of an advanced topic, so I won't get too wrapped up in it. But basically what we're going to do is we're going to define a couple of threads, and threads are basically units of execution that can run in the background, typically mapped to processor cores. And we're going to have those threads play ping pong. So let me first run the program so you can see what I'm talking about. Sadly, this is even less sophisticated than Pong, which was one of the original video games. So you can see we're going to go ahead and have one thread print out ping, and then the other thread will print out pong. The next thread prints out ping. The next thread prints out pong. And they alternate going back ping, pong, ping, pong, ping, pong. And in order to make sure that things actually alternate properly, we're going to end up using a couple of semaphores for this. And it's a little bit beyond the scope of this discussion to talk about what semaphores are. I'll show you the code briefly, but basically here's what we have. We have this method called play ping pong, and you can see it takes 4 parameters. It takes the number of iterations to run, the string to print, and then it passes in 2 semaphores. And semaphores are basically going to be used here to coordinate the order in which things execute. And we're going to basically go for loop equal I, loop to less than or equal to max iterations, and we're going to acquire our semaphore, which allows us to make progress only when it's available. We then print out the string, and then we release the other thread's semaphore. So we're going to that's what we're going to alternate going back and forth. So we're going to do this with 2 threads for a maximum of 4 iterations. So here's what it looks like. We create an array of 2 threads. So we have standard thread. It's basically a wrapper for underlying operating system and C library support for threading. We print ready, set, go. We create a pair of semaphores, and these are what are called binary semaphores. They have a count. They're either 1, which means they're available, or 0 means they're locked. So we have the ping semaphore and the pong semaphore. The ping semaphore starts out unlocked. The pong semaphore starts out locked. And then we go ahead and we define 2 threads. And that's really what I want to show you here is the variadic mechanisms for dealing with threads. So we have thread. This is the first thread. It's the ping thread. We know it's the ping thread because we pass in the ping string. And then we define another thread called the pong thread, which says pong. They both take the same number of iterations. But notice how the semaphore that's my semaphore for the ping thread is the ping semaphore, whereas the semaphore that's the semaphore for the pong thread is the pong semaphore. And the way this set is set up is that the ping thread will get to run first because it starts out its semaphore unlocked, whereas the other guy's semaphore starts out locked. Again, that's just kind of to show you at a high level how those things work. What I want to show you, though, is diving into the thread implementation. And you'll notice thread is not a template class. However, one of its methods, the one down here called thread, which is the constructor, is a variadic template. And you can see it takes 2 parameters. It takes a callable, and the callable is going to be the function that's passed in. So in this case, that's going to be the play ping pong function. So it takes that as one of the parameters. And then the other parameters it takes is a variadic template for all the parameters that need to be passed to the callable. So another way of saying that is all the parameters here, max iterations, ping semaphore, pong semaphore, and so on, all of those things need to be passed to play ping pong. And you can see there are 4 parameters there. And so the magic here is to use C++ variadic templates in order to say there's n of these things that are going to be used. And then if you take a little peek down here and you look at the implementation, you can see what it's basically doing is it's forwarding the callable parameter unchanged, followed by all of the variadic parameters unchanged by using the forward helper method in C++. And then that'll, under the hood, that'll go ahead and invoke the method. I'm not going to go through the details of how that works at the low level. But basically what we're doing here is we're making it possible to have a type-safe way to pass an arbitrary, but at any given point defined number of parameters to the thread function that's going to run in a background thread. Once those threads are basically constructed, they start to run, and then the main thread just sits here and waits for the other threads to finish, and it will join with them when they're all done. I guess just for kicks, I can very quickly show you what the semaphore looks like. A semaphore is a classic synchronizer that's built into many languages. I'm defining this for C++ because they have other mechanisms that you can use to build this. And the 2 methods on a semaphore are acquire and release, also known as P and V. And acquire has the semantics that says decrement this thing by 1, but only make progress if the value is greater than 0. And release says increment the value by 1. And those things have to be done atomically. And the way that works is by using some C++ standard synchronizer classes, a mutex, and a condition variable. And again, it's really beyond the scope of this talk to explain those things. But in a nutshell, we can do this by defining what's called the monitor object pattern, where the acquire method runs in a critical section that's guarded by this lock. And we then use the wait method on the condition variable to say, don't return until the value of n is greater than 0. So that's how we're going to do the atomic acquire. And then the release method is much easier. We grab the lock, we increment the count by 1, and then we notify any waiting thread that someone's released the value. Again, that's really beyond the scope of tutorial on templates, but it's a really cool example. It's an industrial strength style piece of code, and it shows nicely how variadic templates are used for C++ standard template library threads in order to pass a variable number of parameters to functions in a type-safe way. Okay, so those were the topics that I wanted to talk about today. If anybody has any questions, I'll be happy to take questions. If you don't have any questions, I'll give you a quick overview of what we're going to do next. The next thing we're going to start is getting into the real meat of the STL, which is probably why most of you came here in the first place, and that's going to be talking about containers. And we're going to start with sequential containers. We're going to talk about vectors. We're going to talk about decks. We're going to talk about lists. Then we're going to go ahead and spend a little bit of time talking about some other sequential container-like things like strings and bit sets and val arrays and so on. And after that, we're going to talk about iterators. After that, we're going to talk about associative containers. And believe me, there's still way more stuff to come. So there will be plenty of chances to learn more about these concepts. For example, if you want to understand semaphores, I have a whole pile of courses that talk about semaphores. They focus primarily on Java. But I guess, there is a question. Then let me address this question very quickly because it's a good question. Let's go back over here. So if you take a look here at my semaphore implementation, you'll see that when I did the wait, I passed in this. And this is basically a way to say the value n here, which is the one that comes out of the class. If you look back up here, you see that's the data member n underscore. What this is basically saying is this value can be changed. So we're saying, or you can change anything you want in this particular class. If I get rid of this, then I get an error saying this cannot be implicitly captured in this context. So this is what's typically called the capture clause. And right now I'm just saying you can capture anything in this object. There's only one element at this point. I think I can also, whoops, let's see. Yeah, so I think I need to say this. There's other stuff we'll talk about later that have more subtle semantics for what you can put into a capture clause. But basically, that's just a way to ensure that the value can be read, and we're saying I want it from this. Let's see if I can do that. Oh, no. So we're passing in this, and that basically just says n underscore is coming from the object that's invoking the wait. This is very similar to Java's concept of lambda expressions, where you have to use, effectively final variables and so on. This is a way around the restrictions that Java has on lambdas by being able to explicitly capture the context in certain ways. Again, if you're curious and want to learn more about semaphores, which again is, like I said, a bit beyond the scope of what we're covering, if you go here to my, let's see, let's go to digital learning, and you poke around down here and you go to the first link, which is concurrent object-directed programming with Java, and you go down a ways, you'll see that there's a whole pile of stuff here about semaphores. Let's see, where's that start? It's probably actually very early. There you go. Week 3 has a whole discussion of semaphores, and the first video, the first lecture, talks about what a semaphore is in a way that's not really dependent on it being Java. So semaphores are a classic synchronization / coordination mechanism that have been around for probably 50 years at this point, or longer if you consider the fact that they grew out of, train signaling or other types of signal flags, for example. So it's a very classic synchronizing concept. Okay, well, I think that's pretty much what I wanted to cover today. I will turn this into a video here shortly. Thanks for coming. Feel free to ask other questions, and I will look forward to talking to you soon.